Hi everyone, this is Shelby Little, and I'm going to be presenting to you all about quantum dots, a big advancement for solar energy. So first, I'm going to introduce you all with how photovoltaics work, and since the most common solar panel is made from silicone, I will only be discussing silicone solar panels. In this diagram to the right, we can see the layers of each solar cell within a greater solar panel. There's typically a p-doped silicon layer, an n-doped silicon layer, atop this an anti-reflective coating, metal contacts, and finally glass. In the images to the left, I've shown what n-doping and p-doping looks like. At the top, we have n-doping, where we essentially introduce some phosphorus impurity into our sample. While silicone has 4 valence electrons available in bonding, to participate in bonding, phosphorus has 5 valence electrons, so 4 of them will participate in the bonding, while the other is free to move around through the material and act as a charge carrier. In an opposite sense, for p-doped material, we use an element that only has 3 valence electrons, such as boron, introducing an electron hole into our material. What happens when we put these layers on top of each other? The extra electrons in the n-doped material want to move to the positive holes in the p-doped material, which is what we can see here on the left zoomed in circle. This creates what we call a depletion zone, where there's no free electrons or holes. Outside of this depletion zone, we end up with a positive charge on the top layer from those electrons leaving, and then a negative charge on the bottom layer from some of those holes being filled. So we know from our good times in Physics 271 that electric field lines about a point charge extend out from positive charges and towards negative charges. So we end up creating this electric potential that points down, as we can see with the red arrow. We also recall that negative charged particles in an electric field will experience a force in the opposite direction, F equals QE. So this little depletion zone is created near the junction, and after a few electrons move and fill holes, this electric potential is made, which ends up preventing the electrons in the top layer from getting to the bottom layer holes. So now that we've established the setup, how do we get energy out of the system? So imagine the sun emits photons of light and they hit the panel, and when they hit this depletion region, electron hole pairs are created from electrons being ejected. In the presence of an electric field, the electrons are pushed up to the n-type layer and the holes are pushed down because the holes are positively charged into the p-type layer. So we end up between the two, we end up with a buildup of electrons in the top and the holes in the bottom. And then whenever we connect a metal wire between the two layers, the N and the P, because of this potential from the buildup, we get a flow of electrons in the wire moving towards the holes, which is a current. So from all of this, we can see that in order to harvest energy from the system, we need a photon of light to excite an electron out of an overlapping atomic orbital. In other words, we need to observe the photoelectric effect. When it comes to bulk materials such as silicon, we tend to model the energy orbital levels as energy bands using what we call band theory. This band theory is kind of homologous to molecular orbital theory that we've been discussing in class, as the atomic orbitals overlap in bulk solid, and then from this overlapping emerges this band structure, which is specific to the composition of this solid. So for example, the image on the right shows experimental data from the determination of the energy bands in silicon solid material. The top red band we call the conduction band, and then the bottom band we call the valence band. And in order for electrons to be able to flow through the material, or in other words, in order for the material to behave as a conductor, electrons from the valence band have to gain enough energy to overcome the band gap between the conduction and the valence band. So in silicon, we can see that energy gap is 1.1 electron volts. So we would need that amount of energy in a photon to create an electron hole pair. But as we saw in our solar cell, we did not use pure silicon. We used this n-dope and p-dope silicon. So doping is actually how we can control the size of those energy gaps between the valence and conduction bands. So I created this little image on the left to show how doping changes the band structure, and therefore the energy required to excite an electron from the valence band to the conduction band. With n-doping, the presence of phosphorus in our material changes the footprint of the band structure by adding an extra filled valence band close to the conduction band, as seen on the left. In p-doping with boron, we end up with adding an extra unfilled conduction band close to the valence band. In both of these ways, we decrease the amount of energy needed to excite an electron to the conduction band. One of the limitations to this solid material doping is we can only change the band structure according to what element you introduce. Like phosphorus will always create an extra valence band right here, and then boron will always introduce this extra conduction band right there. So, however, this is not a limitation whenever it comes to quantum dot solar cells. So quantum dots are semiconductors like silicone, but they're nanomaterial, they're nanocrystals. Quantum dots and other nanomaterials, they exhibit unique properties and optical and electronic properties as a result of quantum confinement. Quantum confinement is this phenomenon which results from electrons being held in a dimension that's too small to be comparable to a wavelength of an electron, or the de Broglie wavelength. We can see in the image on the left that the types of energy levels we get from individual atoms, which arise from orbital energy. In this case, we excite electrons from the outermost electron orbital to higher energy orbitals. In the middle image, we can see the bulk material band theory, as we discussed on the previous slide. And then we can see if we have a nanomaterial, we end up with this discrete energy levels like we had when we were looking at the atoms. Again, this is due to quantum confinement effect. At the quantum scale like this, we no longer are limited to the addition of certain elements to change our energy levels like we were with bulk silicon. Now we can control the energy levels by simple manipulation of the size of the nanocrystals, as we can see here. So size manipulation is quite simple in real life. Most of the syntheses end up with different sizes by simply letting the reaction proceed at different lengths of time. So what you could do is run a large synthesis, and then you could remove aliquots from the solution, or of the solution from the source that's being heated. The image from the left is actually a UV-Vis absorption and emission spectrums from a cadmium-selenium quantum dot synthesis that followed this protocol. 1 to 10 correspond to different lengths of time the solution is left on heat. When it comes to mathematically modeling this behavior, we find that quantum dots can be best modeled with a particle in a 3-dimensional spherical box model. The image above shows the assumptions for our particle in a 1-dimensional box model, and the equation shows how we had calculated the discrete energy levels for a particle in a 3-dimensional box. Recall that if we're working with a cube, we could pull out those L terms, leaving the quantum numbers for each dimension in parentheses. So looking at the absorption plot, the diameters of the cadmium-selenium dots synthesized were found to be from sample 3 to 10, about 1.62 nanometers to 2.09 nanometers. So what I'm saying is that we see an increase in size from quantum dot sample 3 through 10. According to our particle in a box equation, if we model the quantum dot in a 3-dimensional cube, we expect that as we increase that denominator L, we also increase this energy gap, we increase the energy term, and then we also know that E equals hc over lambda. So if we decrease the energy, then we increase lambda, which is precisely what we see here on our absorption plot. As we increase the size of the quantum dot, we increase the wavelength it absorbed. So as we just saw, although particle in a cube is a pretty good model to apply to our quantum dots, we can see that it likely gives us an overestimate of space that those electrons can be located in. For this reason, a common revision to this model for solving the energy level in a quantum dot is the particle in a spherical box. It's very similar to the particle in a box, same assumptions and all, but instead of the system being located in a box with sides A, B, and C, we now have a system located in a sphere with radius r. So looking at this equation here on the right, we can look at the relationship between the size of the particle and the wavelength absorbed. Again, this energy band gap, the lowercase bg, that corresponds to the band gap of bulk material. So if we have a cadmium selenium particle larger than 10 nanometers, the wavelength of light that is absorbed would be directly related to the band gap of the bulk cadmium selenium, just as like we saw whenever we were looking at bulk silicon. And we can recall that this energy band gap did not relate to the size of the material. It depended solely on the composition of the material. But in this equation, we also see this energy quantum confinement term, the QC. If the particle is smaller than 10 nanometers, it now experiences this quantum confinement phenomena. And we can see that this energy now depends on the size of our material. look at the equation below. So if we look at this equation, we can notice that it looks very similar to our particle in a box equation from the previous slide, but we now have this radial term R, and the masses correspond to the effective mass of the electron and then the effective mass of the hole. So again, using this equation, we can see that if we increase the size of our quantum dot, we decrease the quantum confinement energy, and therefore we increase the wavelength that our material absorbs. Another note to these equations can be used to solve for the radius of a quantum dot from experimental data. So you can measure the max absorption wavelength from a UV-Vis spectrum, and then you can plug that in and solve for the radius of the corresponding quantum dot. So as we know, the majority of the world's energy supply is dependent on fossil fuels, and the grand use of them increases our risk for climate change. This is one of the many reasons why there has been a big shift towards renewable energy, such as solar energy. Of course, we have not seen that grand shift towards natural energy sources, and that's largely due to the fact that our current solar cells are quite inefficient. In fact, the silicon solar panels that you might see around you generally only have 18 to 22% efficiency. This means that the majority of the energy from the sun is not being captured by our cells. In fact, this energy is either being lost to heat, the electrons could be excited and fall right back into their holes instead of contributing to the current, or photons with energy lower than the band gap cannot excite electrons to the conduction band, and photons with energies larger than the conduction band, although they get the electrons to the conduction band, that additional energy is just lost to the lattice. This efficiency problem is where we see quantum dots being a large technological advancement that could push us towards cutting our fossil fuel consumption and switching to more solar energy. When it comes to silicon panels, each photon with sufficient energy to overcome the band gap can only create one electron hole pair. In quantum dots, we observe that one photon can create multiple electron hole pairs. This itself has the potential to drastically increase the efficiency of our solar cells. As we have seen in this presentation, the synthesis is actually quite simple, and the properties can be controlled by changing the size of our quantum dot modeled as a particle in a spherical box. So thank you for listening, and I hope I have helped connect some of the chemistry we've learned in this course to very important real-world applications.